In this lecture, first we will discuss the definition of basis. So let VF be a vector space. We have a vector space V over F. Now is set as subset of V over F, means S is a subset in which member are vectors. So that is, we can say S the S is subset of S is a set of vectors. S is a set of vectors from V. So we have a set of vectors from V, and V over F is a vector space. Then S is basis. We say that set S is a basis of vector space VF. It is a basis of vector space VF. So it should satisfy two conditions. First, S should be S is Li. मतलब S should be linearly independent, and I have discussed what is linearly independent set in the previous lecture. You can visit. And S spans V over F. Okay, so two conditions should be satisfied for to be a basis for a set that should be linearly independent. What is linearly independent? Whenever C1 V1 plus dot dot Cn Vn equal to 0 will imply Ci equal to 0 for all I. This is the definition of linearly independent, and it spans whole vector space. Okay, so that is the definition of basis of a vector space. So now we will prove this result, which is very important, and what it says that cardinality of any basis, whatever basis you choose of a vector space, its cardinality is the equal, means all the bases have cardinality same. Means you can choose any basis, you will find that the number of vectors in that basis is equal. So we prove this statement. Let B1 and B2 be two bases for vector space B over F. Okay, we have a two basis, means what? We have defined the definition of basis. It means it is Li and it should span all the vector space. So this will imply B1 is Li and spans whole vector space B over F. Also B2 is Li and spans a whole vector space B2. Now in lecture 6 you can visit if you don't visit until now. So in lecture 6 we have proved that if B1 is Li and B2 spans whole vector space, okay, will imply B1 की cardinality of B1 will be less than equal to cardinality of B2. Okay, because of B1 is a basis, it will be Li, and B2 is a basis, it will span. We are using only the definition of basis. B2 will be Li, and so B1 will be Li and B2 should span all the vector space because both are basis. So cardinality of B1 is less than equal to cardinality of B2. Okay, and this statement I have proved in lecture 6. Also B2 is Li because B2 is a basis, and B1 is a spanning set, because it is also a basis. Same cause will imply cardinality of B2 is less than equal to cardinality of B1 from 2. So now from 1, cardinality of B1 is less than equal to cardinality of B2, and cardinality of B2 is less than equal to cardinality of B1. So from 1 and 2, what we get? Cardinality of B1 will be equal to cardinality of B2. And so what we proved? We have taken any two bases and proved their cardinality, means number of vectors in both the bases will be same. Okay. Now third thing, we will define dimension of vector space. Dimension of vector space. What is the dimension of a vector space? So it is the cardinality of any basis of vector space Vf is called dimension of vector space. Okay, so number of vectors in the any basis will be the dimension of vector space. So, and it is denoted by dimension of V. Okay, so if we take an example, so if we take R square, it is a vector space over R, and we can show that 1 0 or 0 1, we have two vectors. It is a basis of R square over R. We can show it is Li, linearly independent, and span all the vectors. Okay, so the dimension of R square over R, what will be dimension? The number of vectors in basis. And how many vectors we have? We have two vectors, so dimension will be 2. Similarly, we can write Rn over R has dimension n.